Good afternoon, everyone. Welcome to day one subsurface session. We have 4 rooms running in parallel, all with very interesting presentations, and you are free to move between the rooms. At the end of each presentation, there will be a Q&A session. You can make questions during the presentation in the Q&A chat that you can find in the right side of your screen with the question mark icon. As a moderator, chairman of this session, we will have Dr. Miles Leggett. He is currently Head of Geosolutions at Galp E&P in Lisbon since August 2013. He is an applied geoscientist and an expert in quantitative interpretation, analysis, and seismic reservoir characterization. Dr. Miles started his career in E&P with a postdoctoral stint at University of Glasgow and British Gas Research in 1994, just after receiving his PhD on borehole seismic and tomography from Durham University. He has 28 years of experience with Q&I, working for several companies from Jason Geosystems, Frugal Jason, and Geo Global Resources in Canada, being part of a team responsible for oil discoveries onshore in the Kambai Basin and Krishna Godavari Basin. Please welcome Miles Leggett, and the floor is yours.
Good afternoon, ladies and gentlemen. Thank you, Bruno, for that fine introduction. Good morning and good evening to those who are joining us from other time zones. As Bruno said, welcome to the first subsurface session of this 7th edition of Galp Open Days in a very different format. How times change, but it just shows that we are adaptable. It gives me great pleasure to introduce our first speaker of the day, Carlos Jesus, who works in my team as a geophysicist. He's in the geophysical methods team here in Galp E&P. Carlos has both a BSc and a master's degree from Universidad Federal Fluminense.
Hello, Miles, are you seeing my presentation?
Yeah,
Yeah.
I can see your presentation.
Okay,
the title of his presentation today is Multi-Attribute Framework Analysis for the Identification of Good Porosity Zones in the Brazilian Pre-Salt Reservoir. This was published, I believe, last year in Interpretation, SEG Interpretation Journal. Carlos, please go ahead. The floor is yours.
Okay, thanks, Mike, for the introduction. Good afternoon, all. First, again, let's introduce myself. My name is Carlos Jesus. I'm geophysicist at Galp, and it's a pleasure to be here and to share with you our work in Brazilian pre-salt. So, before I start, I will try to put you in the same page than me to be easy to understand what I'm going to present. Okay, so over the 14, 15 years, we have been working with the pre-salt carbonate reservoir, applying the seismic attribute in order to try to identify the features that might be associated with the presence of the hydrocarbon, such as carbonate mount. But as you may know, it's still a big challenge to apply the seismic attribute in this heterogeneous and so complex environment. But today, I'm going to present a new approach. I mean, it's not new because first approach that we applied was in 2017, first version. And then in 2019, we published Interpretation. Again, this approach, but with new things applying this workflow. And the main proposal is to map carbonate mount in Brazilian pre-salt using the combination of the hybrid spectral decomposition and with geometrical attributes. Hybrid spectral decomposition we'll get into detail during the presentation. This was developed in Galp in 2017. Okay, so I'd like to start with a brief introduction. Try to pass here. Okay. So, mounts represent important geological features of the potential hydrocarbon reservoir in the pre-salt carbonate. And to map this mound below a huge and a complex salt layers may be a big challenge due to heterogeneous environment. Also, the high density of the fault and the fractures and the low amplitude anomaly that represent a good porosity in this case are also one of characteristics of this pre-salt carbonate. In this work, we propose a combination of the hybrid spectral decomposition with the geometrical attribute in order to map this mound and try to map a good porosity zone in this mound. So for this, we divide this methodology in 4 stages. First, we start with preconditioning data, where we apply the structure-oriented filtering and image enhancement. After that, we calculate the seismic attribute, and then we combine some seismic attribute and run the seismic facies classification. Most important, we extract the geobody from the seismic facies classification and calibrate with the wells. We name this workflow as 360-degree approach. We published in 2017, first version in SAG conference at Houston. And in the new version we published in 2019 Interpretation magazine. We have tested this workflow in different fields and where could prove it's very useful workflow. Okay, so the main objective in this work is to identify and characterize carbonate mounds over the pre-salt field, highlighting good reservoir quality. This case is a good porosity zone through the geobody extraction. And these geobodies can be used in the static modeling as a special indicator of the good porosity distribution. So, but before to get into detail about this methodology, I'd like to draw your attention for this analogous situation, just for you keep in mind what kind of things we would like to identify in this work. Okay, so for this work, before we need to define some geophysical criteria based on the geophysical characteristics of our target. In this case, we know that we have a low amplitude anomaly, high density of the fault and fractures, and conic shaped geometry. So, just overview about the workflow that we are using. First, we apply the precondition, and then we calculate the geometrical attribute. Secondly, we perform the quality control using well information when is it possible. As you may know, it's not always that we can do this quality control using the well log and compare with the seismic attribute. After that, we run unsupervised seismic facies classification, and then we select the facies that represent a good part of the reservoir and extract the geobody. After we have the geobody, we can run the cross-check where we compare the geobody distribution versus hydraulic flow unit. And if okay, we go to the next step, and the last step in this workflow, we can do the cross-check with well log. If okay, we stop here. If not, we need to return and see where we can improve the result. In this case, we need to run more than one time in order to find the good parameters for hybrid spectral decomposition. So overall, I'm going to try to explain why I apply some kind of seismic attribute for this study. I use the curvature. Curvature was useful to identify the fractures in the fault zone based on the curvature and the discontinuity in the seismic reflector. Also, the coherency attribute also provides to be a useful to identify high density of the fault zone in the carbonate mount. So acoustic inversion was used basically in order to identify low impedance zone and define the hybrid spectral decomposition cutoff. Hybrid spectral decomposition is used in this workflow because pre-salt carbonate mount typically has low amplitude anomalies, and due to the high density of the fault and fractures, and also these increase the porosity in this case. Okay, all attribute that we run here was focused on in the reservoir interval. Okay, so now I will present the methodology that we have used in this work, and I'd like to start with a precondition. The main objective in this step is to prepare the data before calculation of a specific seismic attribute. And first, as you can see, we are seeing the input data, and then we apply the structure-oriented filtering in order to improve the lateral continuity of the reflector and increase the sign-to-noise ratio, and also improve the fault image. Okay, after that we apply the structure-oriented filtering, and as you can see, we improve the fault delineation. It's a very suitable, and then we improve the reflector continuity. And I'd like to call your attention for spectral analysis in this case, because we try to maintain the proportionality of the dominant frequency and the amplitude, because it's very important for us in this study. Okay, so after that we apply image enhancement. Image enhancement is a kind of a spectral enhancement. Its main objective is to improve the vertical resolution, as you can see in this picture. But in order to calculate correctly each attribute, we are going to use a different input. So for curvature, we use the structure-oriented filtering, because curvature is very sensitive to noise, and also we need to have a control. This attribute basically doesn't consider amplitude change, but due to it's very sensitive to noise, we need to reduce the presence of the noise in this data. And also curvature basically measure the curvature of the reflector. It's very useful to map the fault and the fractures. And then you apply the image enhancement in order to calculate the coherency attribute. Coherency, as you know, is a very traditional seismic attribute where we run the correlation between seismic traces, consider one specific window of the analysis. So, and then we use the structure-oriented filter in order to apply the spectral decomposition, and then hybrid spectral decomposition. So why we use the structure-oriented filter in this case? For calculate the spectral decomposition, because it's very important I maintain the proportionality of the amplitude and more trustable amplitude that I can. So now we are seeing the result where in our left we have the curvature and the right we have coherence attribute. And as you can see here, we can see the highlight some features that we believe that is fracture in the fault zone. And what we can be happy with this result because we have a well on this over this mapped zone. We are seeing the horizon slice from the top of the reservoir, but this attribute was volumetric. We are seeing the only horizon slice because it's a two-dimensional. In this case, it's much easier to present. So in the coherence, it's much easy to see also the fracture zone. That also we have the wells over this fracture in the fault zone. So, and now getting into detail about these geometrical attributes is not necessary because, as I mentioned before, they are traditional one. And I believe I don't have nothing new about those attributes to add here. I will get into detail about the method in order to optimize and apply the hybrid spectral decomposition. So this step was divided in two stages. Stage 1 we can name a sensitivity study, where we are going to analyze the amplitude and the frequency behavior into the reservoir interval. That's the next slide. Okay. First, we calculate the dominant frequency between the top and the base of the reservoir. And then, as you can see in the red color, we can see low frequency behavior in the well location. As red color here, I will try to point out here. And then we identify that we have a low frequency in some zone in this part of the reservoir. And then we run the amplitude RMS. As you can see, we have a low amplitude zone also in the good well location. So after the sensitivity study, we are going to get in detail about the hybrid spectral decomposition. Basically, hybrid spectral decomposition consists of the decomposed data in different frequency bandwidth, calculate the envelope and the differences in this step, and then isolate the specific amplitude range for a specific frequency bandwidth. So hybrid spectral decomposition can be used for identifying geometry, good porosity, and lithology or fluid content. Hybrid spectral decomposition is a hybrid attribute where we use the result of the spectral decomposition in order to isolate specific geologic body based on the amplitude for a specific frequency range. So again, here we have the statistical data as input, and then we apply, for this case, we apply the short time Fourier transform. But for run this workflow, you can apply different transform. And then we decompose the data in different frequency bandwidth, and based on the sensitivity study, we select the frequency that best represents our reservoir. In this case, I have 80 Hz as central frequency. And then I apply the envelope attribute. So in our left we have the spectral decomposition result, where we have in red color low amplitude zone. And then we apply the script where we try to isolate low amplitude zone and just see our mount amplitude, or low amplitude anomaly. And the right, we have the result of the hybrid spectral decomposition. As you can see here, it's highlighted where we have the mount in top of the reservoir in this horizon slice. The good news here is that the good wells are at the good location. So now here though, okay, now we are going to run the quality control for this attribute for hybrid spectral decomposition, where we use the total porosity log. And I need to, before to start this quality control, I need to remember that we are working with 80 Hz as central frequency. We have too low frequency here. So when we are looking this log of this attribute, we need to look for trend, not the tail. This attribute give information, qualitative information, it's not quantitative. So we calculate the silt log of the hybrid spectral composition at the well location, and then we compare with total porosity log with the same scale of the seismic. And in red we have the total porosity log, and in black we have log from the hybrid spectral decomposition. As you can see here, when we have the total porosity increasing, we have hybrid spectral decomposition decreasing. These we can see for different wells. And in yellow, we have what we can say that's the best part of the reservoir. The best part in terms of the porosity. It's very good correlation in this case. So after that, I think we have all attributes that we need ready, and then we can go to the next step. So I want to get into detail about seismic phase classification, because this is subject for another presentation. But I'd like to point out some parameters that I have been used in this workflow. First, we use the unsupervised analysis, because the idea here is run the data-driven workflow, and then I want that the data tell me what is good or not. And PCA with 3 components, and the method used for this seismic phase classification was neuronal, and the number of classes was 5. We test a lot of parameters, but just presented what we got good result. So also we are seeing the in cross line pass through wells, where we can see some features that might resemble amount geometry. Highlight here. Okay, point is better. Like here. So before to go to the next step, I'd like just to remember you about what we propose to map at the beginning of this presentation. And again, I'm repeating this slide where we have the monolake pictorial, where is our analogy. Again, here, so after we run the seismic phase classification, we have the volume that we can try to extract the geobody. So here we can see also again the analog, the picture analog here, and also below we have the seismic phase classification, and we can we can see some correlation between them. So the geobody detection was done from classes 1 to 3, and the limit of the extraction was based on the well mark and the log. So now, for what we name field 1, we have a mount identifier. Good things here that the good wells are at the good location, and the well 4 that is not good, is in shale zone, was not mapped. And again, other is applying the field 2, where also we could map a good porosity zone. So finally, combine geometrical attributes, in this case curvature and coherence, was useful to identify the high density of the fault and fractures, typically carbonate mount. Hybrid spectral decomposition was used because the pre-salt has pre-salt carbonate mount has a low amplitude anomaly for the field that was applying this workflow, and also prove that the hybrid spectral decomposition is very good in order to indicate the qualitative porosity indicator. Multi-attribute unsupervised classification generate. We could see one outcome that based on our analog situation. And after we extract the geobody, we can use this geobody for stacked modeling and use as additional indicator of the porosity distribution. So from my side, I think that's all. I hope I have made myself clear, and any question, I will be glad to try to answer. Thanks, Mike. Finishing here.
Thank you, Carlos, for that very interesting talk. Of course, I've seen a lot of that work before, but I still find it very interesting the way you managed to pull out those mounds from the scientific data. I have a couple of questions myself, but before I do that, I'd like to remind all participants that we do encourage you to submit questions using the question mark on the right-hand side of the webcast there, and you can type in your questions and they'll be sent to me to ask. Anyway, Carlos, do you think the use of broadband data could improve these results if it was true broadband with a much broader spectrum?
Yeah, this question, some partner that like this workflow asking the last time I presented, and yes, I believe that with broadband data we can improve the result, and we can have more confidence in this workflow. Why? Because the first version that we applied this workflow was in 2017, where the quality of the data was not so good like this data that I tested the 2019 version. So based on this improvement, we believe that we can improve this result too.
Also, in the future, we may end up with the OBN data over many of these pre-salt fields in Brazil, and that will give us access to full azimuth data. And do you think that will also add value in terms of, say, fracture characterization, or even discrete fracture networks, for example, things like that?
Yeah, if we have like a multi-azimuth or full azimuth data, and then I think we can improve this workflow using supervised classification, and then we can, because we have more azimuthal information, and we can increase a lot this confidence of this method.
Yeah, I tend to agree with you, and I've got one final comment or question. I see some value in extending this to maybe a more geostatistical approach, or providing probability volumes instead of just discrete answers as input to the static model? Do you think it could be adapted to do that?
Yeah, we need to test, but I think yes. I think yes. Because, for example, we have a main workflow, but for different fields, we need to do different. We need to use different attributes. We need to include some different attributes for example, for bioclassic zone, or what we can name coquina. So based on that, I think we can do we can test to different approach in this case. So, but only test to see.
Yeah, I agree. Thank you, Carlos. I think you've just given yourself work to do in the future. Thank you very much for your presentation and for your contribution.
Thank you.
Much appreciated. Okay, now we're moving on to presentation number 2, and it gives me great pleasure to introduce our second speaker. He's Dr. Paul Wright. He's a principal consultant sedimentologist at PwC, and he has over 40 years experience in carbonate sedimentology. 20 years of that has been in the oil and gas industry itself. He is considered a global expert in carbonate sedimentology, and he teaches applied carbonate sedimentology to classes worldwide, including here in Galp ENP. He has done one of those here for us. He's published more than 140 research papers in international journals, and he has extensive field experience in Spain, Portugal, USA, and Oman. He holds a BSc in geology from the University of Bristol and a PhD from the University of Wales, Cardiff, and a Doctor of Science from the University of Wales. In addition, in 2016, he was awarded the Society for Sedimentary Geology Pettyjohn Medal in recognition of continuing excellence in advancing many diverse fields of sedimentary geology. And in 2015, the AAPG Grover Murray Distinguished Educator Medal. The title of his presentation this afternoon is The Mantle, CO2, and the Giant Aptian Chemogenic Lacustrine Carbonate Factory of the South Atlantic. That's quite a mouthful, but I look forward to hearing Dr. Wright give us a bit more detail about his insights into these giant carbonate factories that have been so prolific in the pre-salt Brazil oil domain. I think he's on his way, so.
I'm here.
Okay. Hello, Paul. Welcome.
Hi.
The floor is yours, so please go ahead with your presentation.
Boa tarde, everyone. Yes, the title is a bit of a mouthful, but
Paul, I think we've lost your presentation.
Hello, Miles. Sorry. We just need a few seconds to Paul Wright to reestablish connection, okay?
No problem.
It's all my fault. It's bound to be my fault.
I think this is quite new for a lot of us here. So.
Do I need to do anything?
Paul, you can start your presentation now.
Okay, and I can work the screen from here?
No, you'll have to tell me. I will switch the slides for you, okay?
Right, have you got... Could you try press the next slide, please? No, I'm doing something wrong, aren't I? Can you get up my first slide, please? I can't see my slides. Okay. Can you all hear me? Yes, I hope. Yes? Okay. Right. That was undoubtedly my fault. These things usually are. What I'd like to do is to perhaps set the scene. We're all familiar how important the South Atlantic fields have been. That's the microbialite, the Barravellia equivalent, and the deeper coquina reservoirs. But I think many people may not fully appreciate just how strange these reservoirs are, and also this strangeness, this uniqueness about them has largely, but not wholly, been the cause of all the controversies and debate. So what I'd like to do is to discuss then the Aptian Barravellia type reservoirs, explain why they're unique, try to perhaps therefore make it clearer why there's been so much debate and controversy, and point out why they're different to all other carbonate reservoirs. And in fact, it seems that they were the direct result of mantle activity, and that they were not in any way the product of contemporary oceans. As most carbonate reservoirs are, they relate to what was going on in the world oceans at the time. But the Barravellia and its equivalents were independent. They were just as alien as if they were from another planet. And the unique characters of the host rock of the reservoir, the actual carbonate host rock, bizarrely, due to the interaction of magnesium silicate gels and carbonate. And those carbonates were largely abiogenic and formed in hyperalkaline lakes. We're talking about lakes which covered at least 1/3 of a million square kilometers, making them probably the third biggest lake system in the whole history of this planet. The major cations that built those limestones, the calcium and magnesium, were largely sourced from continental basalts and older felsic basement, and that those cations were introduced, not precipitated out of seawater as we usually have, but they were introduced via the leaching by CO2 charged fluids supplied from the mantle, leaching out those cations. But that those CO2 rich fluids also produced the alkalinity, the extreme alkalinity that created that reservoir. Now, the release of the CO2 during the formation of those carbonates may have contributed to the onset of oceanic anoxic event 1A, and therefore some of the most important source rocks in the world. And also they may have contributed to the peak marine carbonate production, which we see in the Albion. So in a way, you could argue this CO2 was having a role in producing not only the Barravellia, but also impacting on the formation of global source rocks and global carbonate reservoirs elsewhere. Next slide, please. So we're dealing with then these basins in the South Atlantic that you know so much about, the Campos and Santos and Kwanza. My expertise has been in the Santos. In the Santos, the unit I'm going to talk about is known as the Barravellia, but of course in Campos is the Macabou and has its own names in Kwanza. You may be familiar with the fact that the coquina reservoirs are older than the ones I'm going to talk about. I'm concentrating then on the carbonates which formed during the latter part of the rift and the sag phase. These are very shallow, were very shallow hyperalkaline lakes. They used to be called the microbialites, but that's something of a misnomer. So they are different to the coquina reservoirs, which formed mainly in the active rift stages and were much deeper lakes and less highly alkaline, although they were still somewhat alkaline. Now, the Baravelia from that diagram there may have lasted about 7 million years, but there is a case to be made that it could have formed in a much, much shorter time period, possibly as little as under 100,000 years. Next slide, please. So we're dealing then with the early stages of Atlantic rifting, and initially we saw the development of non-marine water bodies, deeper and then shallower water bodies into the sag stage, which were purely lacustrine in origin. So that would be the Aptian story, and then as you go through the Aptian, next slide please, into the Albian, we see that the marine system pours in and we have evaporitic marine carbonates followed by pure marine carbonates through into the later Aptian. Now, if you look in rift systems today, we have plenty of information about modern rift systems. You can see those elongate lakes on that image there. These are the East African lakes, intensively studied, if only because of our interest in early hominid evolution. But we know a lot about modern lakes and about their chemistry, and we know a lot about ancient rift lakes as well. But none of them that we've looked at bear any close resemblance to what happened in the formation of the Baravelia lakes. So they're different. Despite all this data that we can use, all the analogues we can use, the Baravelia turned out to be much more remarkable than anything we'd seen throughout the whole geological record. Next one, please. The Aptian Albian globally was a time of massive carbonate production. And indeed, if you look, you can see where the star marks there, those are the reserves that are in Aptian Albian carbonates, diagram courtesy of CNC reservoirs. So we're dealing with an interval in which vast quantities of the world's liquid hydrocarbons are stored. Next one, please. And in fact, you can see from the grey area in that graph that the amount of carbonate, neritic, shallow water carbonate being produced during the Aptian Albian was also a peak for the Cretaceous. So it was one of those many peaks during the Phanerozoic when carbonates were just forming all over the place. Now, some of that just represents the bathymetry of the continents and the position of the continents, but it has been argued that that peak there is no coincidence with the fact that there were very high rates of volcanic CO2 being produced in the early Cretaceous. And the link it's been suggested in this very recent paper by Paul et al. Is that the high volcanic CO2 which had been produced earlier in the Cretaceous meant that there was extensive silicate weathering going on the continents, releasing the cations, releasing the bicarbonate ions that went into the world ocean that resulted in this phenomenal amounts of Aptian Albian carbonates we see particularly in the Middle East, but of course they're very important in the Gulf of Mexico and many other places as well. Next one, please. Now, what we see in the Baravelia mineralogically is remarkably simple. We see evidence of primary minerals of calcite, calcium carbonate, and stevensite, this complex magnesium silicate. We see diagenetic minerals, we see quite a bit of dolomite, we see a lot of silica, which does a lot of porosity destruction in the Baravelia and its equivalents, and we see cryolite, which is an unusual sodium aluminium fluoride mineral, and we see a few other things. But if these are hyperalkaline evaporitic lakes, as the evidence suggests, why don't we see sulfates and chlorides? Why don't we see calcium sulfate, anhydride, gypsum? Why don't we see halite and so forth that we see in most other evaporite basins? We do later, of course, when the Cretaceous seawater poured in. Now, in a rather apocryphal way, the American geochemist Tura Serling wrote a little paper in 1994 which said that if you only drain waters, either hydrothermally or by runoff, from a purely basic volcanic terrain, you will not get evaporites, the typical evaporites like the sulfates and the chlorides. You will only get, and his apocryphal Writing said calcite and trioctahedral smectite. Now, Tudor Serling didn't know anything about what we'd find in the pre-salt, but he got this right. His predictions were that just draining a basic volcanic terrain, you would end up with calcite and trioctahedral smectite, in other words, stevensite and similar magnesium clays, and some sodium minerals. If you drain almost any other sort of continental terrain, you will generate to some degree sulfates and chlorides. So he was making the point that in these unusual terrains that you do get locally in the East African Rift, where he was studying at the time, you would get this strange mixture. But no one had ever recorded this mixture in the geological record until we had the Baravelia. Next one, please. Now, we can try and trace the cations in the Baravelia indirectly by using a proxy. We can use strontium and try and identify where the strontium has come from. Now, on that graph there, you can see the green rectangle, and that indicates the strontium isotope values from the Baravelia. And if you drop your eye down to the red box and the green box, those are values which are coming from foliatic basalts, continental basalts associated with the Brazilian margin, which of course are not exactly fitting in that green oblong, but there's evidence also that a felsic, a more acidic continental source, and it would appear, our understanding at the moment anyway, is that the cations coming into the Baravelia, the calcium, the magnesium and so forth, which we're using strontium as a proxy for, because it can substitute into the lattices. The strontium in those minerals seems to have come from a combined or a mix of foliatic basalts, probably comparable to the ones onshore in Brazil and in the subsurface in Brazil, but mixed with a felsic source. What we do know for definite is the cations were not coming from the mantle directly, and they were not coming from oceanic basalts. And they're also really not being influenced very much, if at all, by Cretaceous seawater. So we've got a hint of a basaltic source, but it's being modified. Whatever is bringing in that calcium and magnesium is also interacting with some more acidic rock as well. Next one, please. So texturally what it's made of, I think many of you may be aware that texturally the Baravelia interequivalents, the microbialite reservoirs as they were called, are very, very simple. They're made of crystal shrubs, and you can see the porosity in blue there. They make very good reservoir units. These crystals are made out of highly fibrous, branching, splitting calcite crystals, and from the crystallographic properties, which I haven't got time to go into, we know that they were produced from the very rapid precipitation of calcium carbonate from supersaturated, highly alkaline waters. There's no evidence of any biogenicity in them. They appear to be purely chemogenic. Next one, please. The other key component are the spherulites. These are millimeter-sized radiating clusters of crystals, and they're often associated with, as you can see in the bottom right-hand diagram, with a darker matrix, and that's stevensite or replaced stevensite. Now, from experimental work, we can show that spherulites like this, and there's a substantial literature on this, that was done before the Baravelia was discovered. We know a lot about how these things form. They can form biotically, or biogenically, or abiogenically, but their growth is favored by growing in highly alkaline solutions with very high concentrations of magnesium and silica in solution. They grow by very rapid crystal growth, rapid crystal precipitation, and because they've taken on these unusual textures with the stevensite, they appeared at some point during their growth to have resisted the temptation to simply drop to the bottom of the water column. We don't see any evidence that they were growing on the seafloor, on the lake floor like the shrubs. They were actually being held in suspension in some form. So the experimental work has always shown that these things have to form in a viscous medium. Now, the precursor phase before the stevensite clays formed, the things you can see in the brown color there, was a magnesium silicate gel. So basically, these things seem to have formed in hyperalkaline, hypersaturated solutions, floating within some sort of viscous medium, which was probably a magnesium silicate gel. Next slide, please. And in this case, Thank you. In this case, here we've got the Stevensite partly replaced. Here it's been replaced by talc. And Stevensite it starts off when it's made in the laboratory as a series of nanoparticles. These are highly hydrated, about 20% water by weight. These nanoparticles coalesce to form a gel. It looks like hair gel and it feels like hair gel. Okay, it really is a gel in the way we would think of a gel. And it tends to form when the pH is greater than 9.5. In fact, it was almost certainly greater than 10 when these things formed in these lakes. So these were very nasty, highly alkaline lakes. Within it, the gels formed. Within the gels, the spherulites began to nucleate. And then later on, when the water was driven off, if you like, when there was hydration took place, the gels converted into what we think of as typical clay particles. Some of the larger ones shown there in the bottom image. Next one, please. Now, what is remarkable about Stevensite, and you can see the talc Stevensite on the images on the right-hand side, is that it's soluble under certain diagenetic conditions. I never believed clays could dissolve, and nor did any of the other people I was working with when we did the first studies. But in fact, Stevensite will undergo congruent dissolution and dissolve. What you're seeing on the right-hand side are the large blobs, which are the spherulites, and you see the rather strange draped bridge-like structures between them. They're made of dolomite or magnesite, and then scattered within them are more granular pieces of dolomites. And if you look at the pictures on the left, you can see the porosity, which is good, of course, but the porosity there represents the dissolution, the removal of the magnesium clays. And I simply didn't believe clays could disappear. Clays are one of the most resistant things you can have diagenetically. They can change their composition, but they don't disappear. But in Stevensite and related clays, they do. Next slide, please. Now, without going into the detailed lattice structure, there's a few crucial things about Stevensite. And one of them is that it has virtually no aluminium. Now, aluminium is a very resistant element during diagenesis. It doesn't like to move, it stays put. You can convert one clay to another. You can convert smectite to illite. You can move the cations around, but you can't easily get rid of the aluminium. But Stevensite is a clay which has virtually no aluminium, or none at all. And the Barravelia clay seem to have had less than 2% weight percent aluminium. So once you have lost that very resistant framework of aluminium, it's easy to dissolve clay. In addition, the Stevensite has very weak magnesium-oxygen bonds, so it breaks down very readily. When it does, it goes through a process called deprotonation, where it releases hydrogen ions. In other words, it can produce, as it decays, its own acid flush. Now, we've been aware in the Barravelia for some time that permeability has been enhanced by a late-stage flush of acidic fluids. And this release of hydrogen as the mineral decays may have contributed somewhat to that leaching effect. It's known as the Hoffman-Clement effect. Now, if we look at what happens to the Stevensite on the right-hand diagram, our magnesium silicate precursor breaks down. It releases about 30% magnesium, and we do see quite a bit of dolomite replacement and dolomite cementation, secondary dolomite replacement within the Barravelia reservoirs. We also see a great deal of silica cementation, which is little wonder because Stevensite contains about 60% silica. We see a small amount of cryolite, which fits in rather well with the fact that the Stevensite only had about 3% sodium. So that's what seems to have mopped up the sodium. Hydrogen ions are released. Now, one of the most remarkable things, and you may have noticed this already, the very delicate features I showed you. So if I could go back just a slide, please. And one, that's fine, lovely. You can see on the left-hand side those very delicate magnesite dolomite bridges. They've resisted compaction. So there's something strange going on in the later stage history of this reservoir. If you could go forward one, please. Next slide. Lovely, thank you. We don't see much evidence of pressure solution and compaction in the reservoir. One possibility is all the bound water which the Stevensite was holding on to and finally released when it decayed created overpressure. So it is possible that Stevensite has a remarkable ability to control the formation of the carbonate in the first place, and then go on and control porosity evolution and subsequent diagenesis. It's almost behaving like a closed system. Next slide, please. There are other, back one, please. Thank you. There are other rock types there, of course. We see laminated sediments, which would suggest somewhat deeper water, probably. These are associated with fish and ostracods, indicating that the lake waters were fresher. Something was introducing fresh water into the lakes. And we also see a lot of early diagenetic silica forming, very early diagenetic silica. And that combination of seeing the lake deepening, fresher water coming in, silica dropping out of solution, all fits very well with the idea of fresh water coming in, reducing the pH, which triggers silica precipitation in modern alkaline lakes, such as Lake Magadi in East Africa, and also the fresh waters bringing in the fish and the ostracod arthropods. So these seem to be representing phases of increased freshwater runoff coming into the lake. Next one, please.
Oh, you have 5 more minutes.
Okay, and we also see evidence of grainstones, extensive, well-sorted, wave-dominated grainstone deposits coming in, which Shell have identified as likely shoreline and spit facies. Next one, please. And we have microbialites, but as this slide shows you, in a study of 3,500 plus thin sections from 19 wells and 10 oil fields in the Barravelia, microbial carbonates make up less than 0.5% of the logged core and only occur in between 0.05 and 0.1% of the thin sections. There still is controversy over the lack of microbial textures in the pre-salt, but what is clear from the literature, the microbial literature, is that extreme alkalinity suppresses microbial calcification. So even if they were present in these lakes, they weren't really able to calcify, which explains why the microbialite carbonates are not really microbial. Next one, please. And we have a series of cycles which have been identified in the Barravelia, but if I can just move on to the next slide, please. The idea was presented that these cycles represent evaporation cycles, that we go from a freshwater phase with the fish through to the precipitation of Stevensite with spherulites, through to the precipitation of the shrubs. Now that model was supported by thermodynamic modeling done by Nick Tosca at Oxford, but also the Shell data shows you that the oxygen isotopes are getting heavier, particularly the right-hand column, the oxygen isotopes, are getting heavier through that cycle, which is supporting the idea that these are evaporite cycles. Next one, please. So there's the obligatory block diagram. On the highs, we had fan deltas. On the hanging walls, on the footwall slopes, as Shell has identified, complex spit systems on the hanging wall slopes, and then we pass into these very shallow lakes. Next one, please. Nearly there. Why was the alkalinity so high? Well, the weight of evidence is that these lakes were charged with mantle CO2. Some of the reservoirs today contain about 80% CO2. Some recent ideas have supported the view that Andrew Barnett and I have proposed that it's mantle CO2 because of some studies that have been done by Melisi and co-workers in the Indian Ocean have found that their volcanic lakes are capable of producing large amounts of carbonate and also producing magnesium silicates. And more recently, there are these papers by Peach et al., which is supporting the idea that you're getting a mixture of mantle CO2 and atmospheric CO2 in these lakes, these evaporative lakes. So there's a lot of evidence coming through now that mantle CO2 is capable of and was likely to have influenced these lakes. So the next one, please. Nearly finished. And what about the idea that serpentinization was playing a role in this through exhumed mantle? That isn't supported by the strontium isotope data because none of the cations seem to have been coming from either oceanic basalt or directly from serpentinization. Next one, please. So if we look at marine carbonates where the cations and the bicarbonate are supplied by runoff from the land area, or they're coming ultimately from silicate weathering or perhaps hydrothermally, or typical lacustrine carbonates, where limestone terranes or runoff from silicate terranes are largely supplying the cations and the bicarbonate. What's different about the Barravelia, which we never saw coming, next slide please, is that it seems that with limited runoff and no carbonate source rocks, carbonate rocks in the area to supply the cations and the bicarbonate, the only reasonable source seems to have been from CO2 from the mantle. So a lot of CO2 was coming into these lakes, creating hyperalkalinity, leaching through the basalt, supplying the cations and so forth, and degassing. So these lakes were producing huge amounts of CO2 as that carbonate dropped out. Next one, please. Now, it has been suggested that the carbon isotopes in the Barravelia are reflecting the fact that global CO2 levels were increasing. I would like to turn that point around and suggest that it wasn't that the Barravelia carbon was being affected by the onset of the high carbon content in the atmosphere that triggered the source rocks we see from OAE1A, but in fact, is it possible then that the Barravelia itself was actually contributing to the global increase in atmospheric CO2 that triggered both the production of massive source rocks and also produced all the carbonates that we see, especially coming out in the marine system in the later Aptian and Albion. So last slide then. So there are the conclusions that I've run through. I think CO2 has been a major contributor. It's leaching through the basalts and a little bit of felsic rocks as well, has supplied the cations, and the carbonate to make those carbonates has come from the mantle, and who knows what else this effect has had globally. But the thing that I think always I want to know as a sedimentologist, next one please, my last summary slide, is what would it have looked like if you'd been there? There we've got a seismic line through a Lula tilt block, and we can go to places today where there are half grabens poking through salt flats, and that is about as close as my image of what it would have looked like when the Barravelia reservoirs were forming, within, in this case, two half graben basins separated by an active tilt block. That's from the Great Salt Lake region in Utah. Sorry about the complications at the beginning. As I said, I'm probably sure it's my fault. But anyway, I don't know if we've got time for any questions, but thank you for your listening. Thank you.
Well, thank you very much. Yes, some complications at the beginning, but as I said, we're all learning with this this new system. Not many questions. I just got one here from one of my colleagues, Joe Plunkett. Is it logical to use classic marine carbonate classification terms such as Dunham's, grainstones, etc., to describe the grainier sediments, for lack of other accepted terminology?
I think there are issues about using Dunham for many of the textures. Dunham is based on the idea of texture maturity, and that doesn't work if the grains are growing within a matrix. But in terms of using the term grainstone, I think that's perfectly valid. In fact, Andrew Barnett and I have published this year a paper discussing the terminological problems and the dangers of using Dunham, because if you use Dunham terms for some of the rock textures in the Barravelia, it leads you down a sort of thought pathway to misinterpret the terms. But I think using grainstone for some of these fantastic super mature wave-dominated shorelines in the Barravelia is perfectly valid, yes.
Okay, thank you very much, Paul. I'm afraid we don't have any more time, so thank you for your presentation. Very interesting, and I'll continue to follow your work in the future.
Okay, thank you. Bye-bye.
Let me put come on. Our third speaker today is Angelo Ricciato. I hope I pronounced that correctly.
Perfect.
And he's currently employed as a general geoscientist and technical coordinator in GEPlan Consulting. He has more than 10 years experience in oil and gas, and he works in integrated studies aimed at understanding hydrocarbon potential in naturally fractured reservoirs in both compressional and extensional regimes in various basins around the world. And he does this by looking at various different data sets, subsurface and integrating surface data such as remote sensing information as well. So it's quite a complex workflows that he approaches the problem from. And the title of his presentation today is Approach to the Characterization and Modeling of Complex Carbonate Reservoirs Along the Atlantic Margin. Angelo, the floor is yours. Thank you.
Thank you, Miles, for the introduction. Good afternoon to everyone. And first of all, I would like to thank you, Galp, for this opportunity. I'm going to share my screen now. So please confirm if you see it. Okay, can you see it?
Yes.
Yes, we can.
Okay, good. Thank you. So, as Miles said, I'm an exploration geologist now working the business development of my company, and I would like to briefly introduce the company for whom I work with too in the first couple of slides. So we are a consulting firm that is based in Italy, in northern Italy, and was founded in 2003. We essentially provide the G&G services to E&P companies trying to solve their problems. We have quite a remarkable experience in the characterization of the complex carbonate reservoir, working in different carbonate provinces around the world, worldwide. And we also do training course. We run training course, in-house classroom course for independent national oil companies and association. So what we offer is a wide range of services from surface to subsurface at a multi-scale level. Our team has experience, the main focus are carbonates, however we have been working in clastic as well. In the carbonate reservoir, we have been doing a project from the Proterozoic to Cenozoic target in Europe, Africa, Asia, and America. The team, the multidisciplinary team, is able to work from one well study, single well study, to full field range of activities and services in order to provide integrated studies from surface to subsurface in a different phase of the field life, from exploration to appraisal and development. What we essentially provide at the end of the day is a geocellular 3D static model of the reservoir that can be used as an input for the dynamic modeling and then history matching and so on, in order to calculate and evaluate as much as we can the resources. So these third slides show a bit what is our experience, hence the process of getting knowledge or skill from doing, seeing and feeling things. So I thought that it was important to show all the places where our team has worked. As you can see, the Mediterranean is a quite clustered place full of points. That we moved to Middle East, North and South America, in Europe. And I want to highlight the projects that were carried out along the Atlantic margin, the west and the east. So this was just a brief introduction in order to go directly into the main topics of this talk. So the presentation is divided into two parts. The first one, we'll have a look at the complex carbonate reservoir, the carbonate rock, let's say in general, focusing on the complexity and heterogeneity. Then what is the reality of these complex rocks, the challenges in dealing with the complex carbonate plays, and then which are the main objectives of the modeling. The second part, I would like to show you a case study along the East Atlantic margin in southwestern Barents Sea. So I'll have a brief introduction with the regional setting. I show which is the reservoir, the main challenges that were encountered that actually follow here in the agenda, that are the karst, and then the fault and fracture characterization. Then I'll show you the tools that can be used essentially to model both karst and the fault and fracture. In the case of the fault and fracture, our workflow for the GEPlan modeling. All the results collected during this project and actually achieved during the project has been used for the strategy of appraisal and development of the field. Finally, at the end, some takeaway messages. So, as a first thing, I will start from what the definition of complexity from the Cambridge Dictionary. It's a very easy One that is the state of having many parts and being difficult to understand of an answer to. And the complexity in general characterizes the behavior of a system or model whose components interact in a multiple way and follow local rules. I thought that this was the best definition for carbonate rock, because in the picture that you see in the middle in this slide, that is a slab core, you do see, in fact, in a very small area, because this is a 20 centimeters slab core, you do see how the things change very rapidly close to each other. I mean, we have the matrix that is impregnated of hydrocarbon here. We do have matrix similarly, very close, but different in terms of probably composition, but also of porosity. Then we do see a fracture here, and apparently seem closed or cemented. But if we move down, you see that the fracture is filled with oil, and oil is not continuously present all along the fracture, but only in some points. The last is these bugs. I see a bug that is apparently open with oil inside, and another bug that is probably coming from a fossil that was inside here, that is filled with cemented, probably some precipitation of cement, carbonate cement, and so on. So this is just to highlight the fact that carbonate reservoirs are characterized by extremely heterogeneous porosity and permeability, and these heterogeneities are the cause of a spectrum of environments where the carbonates are deposited and then be affected by subsequent diagenetic alteration of the original rock fabric, leading to a series of challenges that we should deal with. So in the end, we can summarize the different factors that characterize carbonate reservoir as the depositional phases, the architectures, the diagenesis, the petrophysical properties, the fault and fracture and the fault and fracture and the mechanical properties, and the fluid types. This is to say that we do have we would need a variable different data set and also mindset able to approach the issues of carbonate reservoir also from different point of view, and trying to integrate all these different aspects within trying to summarize it within a model. That is the challenging part of our mission. So what is the reality? The reality is that carbonates are not as we are told or we imagine or what we see. When we start to look into detail at carbonates, there's always issues and challenges that we need to face. The reality is too complex. It's difficult to predict because of the nature of its variability and the complex relationship between the processes. The models on the other side are too simple because we have limitation with the tools that we have, and of course we are human. Without everyone with his limitation, and data very often are limited. So we have not enough information to make general statement and fill the gaps. So the objective at the end of the day will be to reduce as much as possible the uncertainties of our carbonate reservoir. So if we look at the history of a field, or actually in the exploration and development of a field, we do see that in the exploration, the pre-drill phase, we have some challenges that we have to tackle. That could be the internal architecture, the structure, and the formation. This can be approached and the risk through some tools that are the regional geology, the paleogeography and GD maps, the outcrop analog, the conceptual model, and a series of other tools that can help in unravel these challenges and solve somehow with a certain degree of certainty these challenges. Once we do our well, so in the post-drill, during the appraisal and development phase, we can say we do come in contact. We do face other type of challenges regarding the diagenesis or either the paleocast, the complexity of the reservoir, the fluids, and then the modeling and the forecast of our reservoir. These challenges can be de-risked by using other tools as core logging, well data, dynamic data, outcrop analog, seismic attributes, and so on. So when we talk about complex carbonate reservoir, in terms of modeling this reservoir, we normally deal with two components, the matrix and the faulting fractures. So in the reality, these two components, of course, are combined in a single body. What we will need is to create an approximation of the model and try to separately understand the porosity permeability of the matrix and the porosity permeability of the fracture and put them together into our model, because the flow behavior in this kind of reservoir reflected the interaction of these two components. Let's go directly to the case study. In the case study, we actually selected a place that is included within those areas of potential interest for Galp. And so we are, as I said, in the Barents Sea, actually in the southern western part of the Barents Sea, here offshore Norway. This area, from a regional setting point of view, has been dominated by three main reef phases that establish actually the architecture, the current architecture of the area, which is characterized by an alternation of fault grabens and the interbasinal highs, which actually control all the evolution. Here we do see the late Paleozoic basin, the Jurassic basin, and the Cretaceous with different color. The rifting, in fact, result in this basin then filled with continental clasting, carbonates, and sea reef deposits. The target that we'll look at today is actually a lower Paleozoic fault-bounded structural high in the Barents Shelf that is between Greenland and Norway. That is actually an element of the Atlantic Rift Farm between the Greenland and Norway during the late Paleozoic. What is the story of this field? So at the beginning, the first well that was drilled discovered oil and gas in the Paleozoic carbonate. Then the company decided to drill another well, number 2, to appraise this discovery. But then they went out of structure inside the basement. They tried with a third well, but they encountered drilling issue. They re-entry. They do some sidetracks. Of course, the experience allowed us to collect evidences and observation during this phase, and they noticed strong mud losses, huge bit drops, occurrence of cavernous formation, and huge bugs in the cores. So in this, on the right, Nelson chart showing exactly the relationship between the matrix porosity, the porosity and the permeability, we do see the different type of reservoirs. I think that everyone is quite familiar with this. Reservoir that where porosity and permeability are affected mostly from rock fractures, from the fractures, and other on the bottom left that are where the porosity and permeability is affected by the rock matrix. Well, in our reservoir, considering the observation that were made, we thought that we're probably between a type 2 and type 3, where we have fracture permeability, and then we have also magic porosity based on our observation. Well, let's have a look at more data. So these logs that we are looking, in fact, the analysis of the log show some two main challenges. We notice that the resistivity tends to be very low in the first part of this extract of the section, and we do see from the image log a bit which are the images of the image log, and that we have interpreted as probably karst, related to karst. We have these huge caves and that are actually corroborate, but these data, we do see very few fractures. These tadpoles are an example. Actually, the tadpoles, the fracture intensity, is very low. But then if you move to the lower section, we have a generally high resistivity, but with peaks that are probably related to conductive fractures. So in fact, if we have a look at the image log, we do see a multitude of fractures and a lot of change in the tadpoles and in the intensity of the fracture. So we can actually identify two main system facies. One is that is more vaggy, one that is more tight. So one issue would be the palocast, and one issue would be the fractures. How we can we model these two challenges, as we can call it? Well, for the cast is a bit problematic. We are in the offshore. We do not have we have our control point are the wells. We do also have the seismic, of course. It was a very good seismic that can show some of these features. However, we decided to go in the outcrops to see some analogs close by to have an idea to how we can model the paleocast in the area. So we mapped in this quarry that you see in this picture the main horizontal and vertical structures and the caves. We took some measurements, we made some statistical analysis of this cast area, and we built a cast conceptual model. Then we use as an input for our cast model where we do see the area with the cast and the area with no cast. Of course, the model was implemented with some of the seismic attributes that were computed using the 3D seismic in order to have an upscale permeability model that can be implemented and integrated with our reservoir model. So the cast, let's say, it was a more kind of speculative approach, but it was within the only one that can be used together with the seismic again to model these the paleocast in the field. The other,
5 minutes.
yeah, sure. I'll try to move faster. The other is the fault and fracture characterization. So the understanding of the fault and fracture network. So we look at the fault and fracture at different scales, from regional to reservoir scale. We compute a series of discrete fault network, and then we upscale and calibrate the different GEPlan scenarios for generating porosity and directional dependent permeability static properties of the fractures for the dynamic simulation. Well, this is the workflow that we use. It essentially summarizes what I just said. So we do have this data set that we see at a different scale, regional scale and a reservoir scale. So a series of data that we can combine to characterize the fault and fracture. So the geometric characteristic of the faults, the geologic evolution of the structure, the factors controlling the fracture development, and the present-day stress field to see which are the stressed fracture sets. Then we build a conceptual model that will be used as input for the discrete fracture model. Then we combine these two models for extend and expand the fracture properties once calculated. This is available data set from large to small scale to structural scale and the present stress field. If we start from the large scale, these are the main tools that we use, of course, for the characterization, so the seismic interpretation, the fault network, and then the seismic attributes. The 3D seismic, the good quality of the 3D seismic allow to make a very detailed interpretation of the fault system. However, we apply some criteria for the fault that will be used in the GEPlan modeling. So we decide to have a reasonable length of more than 100 meters, and appreciable displacement of the amplitude seismic. The interpretation done in the seismic was then also integrated with, as I said, the seismic attributes. These are the suite of attributes that were used: the minimum similarity, the structural smoothing, the variance, and the untracting, in order to extract more information, more data, and more faults for our model. At the reservoir scale, we'll be using coarse image log that you already see before. In the image log, we analyze the fracture density, which are the main sets in the reservoir, and all this information become integrated for the modeling. As you can see, the coverage we had 8 wells, more or less, with core and logs, so we had a quite good coverage of the whole field. And also, we try to understand and to collect data on the aperture of this fracture, because as we know, it's a quite challenging parameter, the aperture, because it could be affected by the burial, the cementation, and so on. So it's quite variable. However, we try to estimate from image logs, but the sensitivity of the absolute aperture was large. Also from the course, looking also at the fielded fractures, and then from the literature. This is an extract of the conceptual model at a larger scale, so shows the large fault and fracture scales to the left, and then the background fault and fracture in the formation of interest. for our of our reservoir target. Another important part was the understanding of the present-day stress field in order to collect indication of the critically stressed fractures and in which mode they were stressed. So again, image log through borehole breakouts, the analysis of the new fracture, and then again, literature data at more regional scale that are always helpful. This is just to show the simplified, because it's a simplified geomechanical model that allows to understand the mode of the fracturing for each fracture set, to evaluate the fracture aperture, and constrain the relative fracture aperture between the fracture set and the DFN inputs. These are the inputs for the DFN. We are almost at the end, so we have faults from the seismic interpretation, fractures from image log data, as I show in the previous slide. These data have been combined together and upscaled in a P32, that is the area of fractures per unit volume of rock mass, intensity log, for the entire grid and for the three sets that were identified by interpreting these data. Of course, there are no references for these models, but just for you to show the final DFM model, then distribution of porosity and the permeability inside the grid. Why we did that? Because, I mean, as we said, the discovery was there. The company wants to understand how to appraise the field, and also how to build the future strategy for the development of the field. So in this case, all this information allowed us to actually change our point of view, and also our technology from the jelly donut old way of drilling, that is basic vertical penetration with limited formation content, to the tiramisu way of drilling, that is trying to catch as much chocolate as possible with sophisticated horizontal permutation and extensive information content. And this way can be done by using integrating the data that we collected, because we have the fracture set orientation. We know which are the open or in shear mode fractures that we can intercept in order to increase the productivity, drain wider reservoir section, increase the recovery factor, and understand the lateral availability of the fault and fracture network. So my takeaway message are that the carbonates are special because their complexity, heterogeneities are associated to the sedimentary basin, to the sedimentary process, and to the deformation style are a lot and variable. And the fact that the realizing and prioritizing the heterogeneity is the priority and the biggest challenge in the reservoir characterization. In the specific, the fault and fracture are actually their development is a consequence of these heterogeneities and the mechanical properties of the carbonates rock. So the understanding and modeling of the fracture and integration into a full field model is a key to plan the development of these fields, so to pass from the jelly donut to the tiramisu way of drilling, to properly model the distribution of hydrocarbons and reduce their sensitivity estimation, but also to collect more data on your reservoir. Thanks for your attention. That was my last slide. And yeah, if there are any questions.
Angelo, thank you very much for the interesting presentation, and just highlighting again how complicated carbonates are. And it's a big challenge for everybody who's trying to study them and plan wells and develop fields. Question about the data that you use. Have you thought about using, for example, an elastic inversion to provide maybe a Young's modulus or other attributes that you could incorporate into your analysis?
The elastic inversion, sorry?
Have you thought about using elastic inversion to add more data into your analysis? For example, it could provide Young's modulus that could add information about how brittle the rocks are, and then you could incorporate.
Yeah, I see your point. Yeah. It was a good question. It is something that we normally do. Actually, we have done in other projects, but not actually in this one. Okay.
Yeah, I think it would add a lot of value, and we certainly see that internally too. Also, one more question. do you have any experience in using full azimuth data for fracture determination or fracture orientations, or is that something you're planning to do in the future?
I think that this was something among the recommendation that we did actually for the client in this project.
Okay, perfect.
Yeah.
Thank you very much for your presentation and your time, and I hope you enjoy the rest of the sessions.
Thanks to you. Thank you.